Hello students. In my previous lecture, I discussed the various methods of speed control of DC motor, armature voltage control, field control, and armature resistance control. We discussed in detail the armature voltage control, but today I will discuss the field control method in detail. So, you recall the equation: speed is given by V upon K phi minus Ra upon K phi square into torque. So we are now changing the flux, keeping the voltage constant, keeping the armature voltage constant. We are not changing the flux produced by the field winding. So you can see that it is in the denominator. So if you decrease the flux, the speed will increase. You cannot increase the flux beyond the rated value because it will lead to saturation and overheating of the field windings. So we can only reduce the flux. So reducing the flux will increase the speed of the motor. And you can see there the characteristics of the DC series motor changes like this. For rated flux, this is the characteristics. For smaller flux phi 1, this is the characteristics. And for further smaller flux phi 2, this is the characteristics. And if it is supplying a constant torque load, the speed will increase from omega mr to omega m1 to omega m2. So in that way, speed can be controlled by decreasing the flux produced by the field winding. Now, same you can see in the separating circuit DC motor. Here, you can notice that the slope of the characteristic is also increasing as we decrease the flux. The no load speed changes as well as the slope will also change. You can see from this equation that if we change the flux, reduce the flux, the no load speed will increase as well as the slope of the curve will also increase. So the speed regulation will become poorer at higher speeds, as the slope of the characteristic is now more than what it was for the rated conditions. So this is a drawback as compared to armature voltage control. There the characteristic was parallel to itself. As we decrease the voltage, the speed regulation remained same. The nature of the characteristic was not changing, but here it is changing. So again, if you are supplying some load torque, you can see that the speed will change from omega mr to omega m1 corresponding to phi 1 and to omega m2 for the flux phi 2 which is less than phi 1. So in that way speed can be controlled. Now one thing you should remember that the current drawn by the motor depends on voltage minus the back EMF, that is Ke phi omega m upon Ra. So if we reduce the flux suddenly, what will happen? Speed will not change instantaneously. So what will happen? The current will rise to very high value. So you have to change the flux only in small steps, or you can change the flux only gradually, so that during the transient period current does not cross the permissible limit for the motor. That is usually twice the rated current of the motor. Now if suppose the motor is supplying rated torque at rated flux. So suppose this is a condition here. The flux is rated flux, the torque is rated torque. Then we have reduced the flux to say phi 1 to increase the speed of the motor. Then what will happen? At the steady state condition, when the speed settles down to the new value, then what will happen? If the load torque is constant, then what will happen? The new torque that is equal to Ke phi 1 Ia1 will be same as the original torque, that is Ke phi r Ia. I have not written in Ke. So phi 1 Ia1 will be same as phi r Ia if the load torque is constant. This means that the current, now the motor will draw, Ia1 will be equal to phi r upon phi 1 into Iar. As phi 1 is less than phi r, Ia1 will be more than Iar. This means that current will be more than the rated current of the motor. And you cannot pass the current higher than rated current for long time, because it will cause overheating in the armature winding. So what you have to do, you have to reduce the load torque if you want to run the motor at a higher speed, and you want to control the speed by reducing the flux. So this means that to limit the current, the load has to be reduced. Or you can say that the motor cannot supply the same torque at higher speed. Or you can say that, in other words, the torque handling capability of the motor will reduce. So this is one drawback of this method. Now let us see what are the various drawbacks. Number one, speed cannot be controlled below the rated speed. Usually we want the speed controlled below the rated speed. So by field control method, you can only control the speed above the rated speed, because you cannot increase the flux to reduce the speed. Second, as I discussed here, the torque handling capability of the motor reduces. Unlike the armature voltage control, there the torque handling capability remained constant. At whatever be the speed, the motor can still provide the same torque, because torque is given by phi into Ia. We are not changing phi. So at rated current, the motor will still supply the rated torque. But here in this case, as we are reducing the flux and current cannot go beyond rated current, so the torque produced by the motor will reduce. So the torque handling capability of the motor will reduce in this case. And the third drawback is also important, that because of armature reaction, because of armature reaction, the flux density wave is distorted. It is not flat type, it is having some peak, it is distorted. And in normal design of the motor, we take care that the armature reaction of the field is higher than the armature reaction of the armature, so that the effect of armature reaction is not severe. But here what we are doing is, armature reaction flux is constant at rated current, but the field flux is now being reduced. So the field flux becomes small as compared to armature reaction flux. So the effect of armature reaction pronounces, or you can say that the flux density will become more peaky. It will increase the iron losses, as well as it will cause problem in the commutation of current. So this is the third drawback of the field control method. Now let us see what is the power and torque capability of the motor in these two speed control methods, that is armature voltage control and field control. So as we discussed, that below the rated speed you have to control the speed by armature voltage control, and above the rated speed you have to control the speed by field control method. So this curve shows here we are having this range. The speed is shown here. So below the rated speed, this is rated speed. Below the rated speed, if you want to control the speed, you have to change the armature voltage, keeping the flux constant. So this black shows flux as well as torque, and this blue line shows voltage and power. So below the rated speed, if you want to change the speed, you have to increase the voltage. If you want to increase the speed, you have to increase the voltage. So you can go up to rated voltage. So this actually is the rated voltage here. So you can increase the voltage from 0 till you reach the rated voltage. Beyond that you cannot increase the voltage. So during this period, the motor can the flux is kept constant. So if the torque produced by the motor will remain constant. Torque is equal to phi into Ia. If you are having a constant torque load connected there, then the torque is equal to phi into Ia, that remains constant. Motor supplies the same torque starting from near 0 speed to the rated speed. So torque capability of the motor remains constant, while the power produced by the motor will increase. Power is equal to V into Ia. This means that the power produced by the motor will increase, but the torque produced by the motor will remain constant. So in this range, the power increases and torque remains constant. So if you are controlling the speed by armature voltage control, that drive you may call as constant torque drive. Power varies, but the torque remains constant. Now beyond that, if you want to control the speed beyond the rated speed, then you have to keep the armature voltage constant at rated value, and you can reduce the flux to increase the speed above the rated speed. So beyond that, you start reducing the flux, keeping the voltage constant. As you reduce the flux, the torque capability of the motor will reduce, because torque is phi into Ia. So phi is reducing, so torque will also reduce. So the torque produced by the motor will decrease, while the power drawn by the motor or power produced by the motor will remain constant, because power is equal to V into Ia. So power remains constant, while the torque produced by the motor will go on decreasing at rated current. So this means that the field control drive you may call as a constant power drive. The torque reduces, but the power remains constant. So the field control drive is called constant power drive, while the armature voltage control drive is known as constant torque drive. So this is an important thing that you must remember. So that is now we should discuss how to implement the field control method. What are the ways you can implement the field control method? I will discuss it just now. Now let us discuss how to implement the field control method. So let us first take the case of separated excited DC motor. So here the field winding is given separate supply. You have to vary this current to vary the flux. So what you can do here, you can connect a small power variable voltage supply, because the power involved in the field winding is very small as compared to the rated power of the motor. It may be less than 1% of the rated power. Machine is suppose of 100 kilowatt. The power required here is only 1 kilowatt or less than that. So less power rating variable voltage supply will be required here. So you can connect here some thyristor bridge. By controlling alpha firing angle, you can control the voltage here, and you can control the current flowing through the field winding, and you can change the flux. So this or you can, even for a smaller motor, you can simply have a rheostat, and from that rheostat you can make a potential divider, and that will do the job. If it is a shunt motor, then you can connect a resistance in series with the field winding and apply rated voltage here. By varying this resistance, you can vary the current flowing in the field winding, and you can control the flux produced by the field winding. So in that way you can control the field current, and hence the flux, and hence the speed of the motor. In the case of series motor, as you know, the current drawn by the armature, this Ia, depends on the load torque. So this is not in your control. So Ia you cannot control independently, because Ia depends on the load on the motor. So what you have to do is you have to vary the flux. So the flux produced by the field winding will depend on number of turns, that is MMF I into N. So one way is using tapped field winding. Instead of a constant one field winding, you have different tappings. So if you connect the terminals here, only this much winding will be there. If you connect it here, the first position, then the whole field winding will be in the circuit. So the current produced by, suppose current is constant, so the flux produced will depend on Ia into this all number of turns. So if you change the tapping to the second position, then what will happen? This much number of turns will be out of circuit. For same current, the number of turns are reduced, Ia into N will be lower, and that will cause decrease in the flux. Further change to position 3 will further lower the flux, and further change in the tapping here will further lower the flux. So in that way you can change the flux produced by the field winding, and hence you can change the speed of the motor. And the other way is that you can connect a shunt resistance across the field winding. So the current that is drawn by the motor or supplied by the power source here will be divided into two parts. One part will go to the diverter resistance, we call it ID. The other part will go to the field winding, let me call it IF. So this IF will depend on the resistance of the diverter resistance RD and the resistance of the field winding. So you can say that the current flowing in the field winding will be equal to IA multiplied by this RD upon RF plus RD, diverter field resistance, RD upon RF. So the field current will depend on what is, I think it will be equal to IF upon RD. No. It is IA multiplied by the resistance RD upon RD plus RF. So by changing the diverter field resistance, you can change the current flowing through the field winding. Lesser is the resistance RD, lesser the current is the field winding. So by reducing RD, you can decrease the current flowing through the field winding. So in that way, you can change the current here, and that will change the flux produced by the field winding. So in this way, you can implement the field control method in series motor. So that is all for today. In the next lecture, we shall discuss the third method, that is the armature resistance control. Thank you for this.